Hello everybody, this is Dr. Hassan again in Renewable and Sustainable Energy. We're still in Module 2. This is the last part of Module 2 and we are in week number 6. We're going to discuss the thermal collector and photovoltaic thermal system. Now, as you know, a huge amount of energy coming to our planet from the sun, and we discuss the situation on the sun where we have insolation around 1360 watt per square meter, and it's captured by the 1/4 of the or let me say 1/4 phases of the earth at an instant of time. And this amount of energy is really huge. If we know how to capture it, how to utilize it, then we can use it for many applications. As example, generate electricity, heating, cooling, lighting, and so on. Okay, now for heating, we discussed the light, how we use it in photovoltaic. Now our discussion here in using the heating part, heating element of solar energy, and it can be used in many applications. And heating can be captured on low or medium or high level. And if you look here, okay, in this graph, okay, this graph, the world energy consumption between 1990 and 2040, as you can see here, nuclear, renewable, coal, natural gas, petroleum, the energy requirement or demand increase with time. But for part of it is renewable energy. It seems to be is gonna be around 50% of the highest one. So more type of renewable energy coming on. One of them is solar thermal energy. Solar thermal energy, we see that there's a huge applications going on in the world. Okay. Now the heat captured could be used to cool a swimming pool, domestic water, low temperature heat for space and heating, building process, electricity generation, for many applications. Before we start talking about these applications and the design, their technical aspects, economical aspects, I just want to let you know we are going to deal with thermodynamic quantities. Okay, so heat, which is usually represented by Q, and heat flow. Then let's see, these are the constants. As you can see, we name them. Okay, you see always we use lambda, but for different let me say parameters. Now if I come here, you can see that we need to know how much the water consumption, hot water consumption, as example for heating water at homes, how much the water consumption by person. Okay, we can find first of all the heat flow. Heat flow is if we integrate it with respect to time, we go the heat, the total heat needed. This formula have been discussed early in this semester, and we have example where we say that the heat required is heat capacity times mass and delta theta or delta T temperature difference. Okay, and this equation contain two variables, contain M and theta. As you can see, C is constant. So when we differentiate to find Q naught, differentiate with respect to time to get the heat flow, C always constant, but we differentiate M with respect to T, keeping delta theta constant, or differentiating delta theta keeping M constant. Okay, now heat capacity is related to the material we use. As example, as you can see here, you see aluminium, iron, ethylene, and different material. Each one of them has its own, let me say, heat from material to material. Now for heat flow through wall, as example, layers, if we have layers, or let me say wall of our houses, this is output temperature. Sometimes it's approaching 40-50 Celsius, and inside you want it to be 50. You need to know the layers here is if it can handle this heat. It's isolated and can handle this heat. I mentioned for this once when I talk about different collector, but it's good to mention them here again. Have a look. Coefficient of heat transfer usually calculated. This is the coefficient of heat transfer. Okay, for layers. Okay, calculated by this formula, and this formula contain alpha, contain S, contain lambda. Alpha 1 and 2 is surface coefficient of heat transfer. Okay, and lambda is thermal conductivity, while SI is the layer thickness. Okay, so see the layer thickness from here to here. Is it, let me say, 10 centimeter, 20 centimeters, okay, and so on. it specify how much heat flow will come from here. This is very important for people working in buildings. Okay, you know, they know they need to know the specifications of heat transfer from outside to inside, because this will specify how much cooling we need, how much energy we need. Our students design solar water heater. As you can see, it's very simple. We mentioned for it before how they what it's contain. It's contain sheet pipes. As you can see here, these are pipes inside, and painted with black to capture more energy. We put the glass on the top to contaminate energy, and water coming from here as example input, going out output. We can save it in a container here. And they did experiment for 1 day from 9:15 into 17:15, and this is the temperature for T in and T out. As you can see here, T in here, T out here, the temperature increase. It's get heated by the sun. And if we want to compare its effectiveness, costly effectiveness, I will compare here. They did the calculation for the same amount of water needed. Okay, as example, electrical water heater for 6 persons or 4 persons. Okay, and these are the years they want to see the annual cost. Okay, there's specific formula to do this, and they found that if we start at year number 1, the cost will increase with time, with years, because we are consuming electricity and we pay for them. But if we compare 6 persons electrical water heater with 6 persons solar water heater. Solar water heater, you can see the green one here is a constant through the time. Its cost, it will not change. Once we pay it, that's it, done. While when we come to electrical water heater, after a while, here it is cheaper at the beginning when we buy it, but with time, after another 3 to 4 years, its cost start to be over than the electric solar water heater. Why? Because we are paying for electricity, and this is added to the total cost. So this tells me that the design of solar water collector is cheaper than, and its use is cheaper than using electrical water heater. Our student, this example from their work, they calculated they want to calculate the collected heat from the designed system, their system, and they try to do the calculation for 1 kilogram per liter, or kilogram, 1000, sorry. Volume is given here, the diameter of the pipe, the length of the pipe, the number of the pipes, and the heat capacity of water. And they did simple calculation here. As you can see here, the volume is a cylinder, okay, multiplied length by number of collectors. Then we have, this is the in cubic centimeter or liter. Okay, now we want to see the mass density by volume. Now here the density given, the volume given, calculated already, we have here in kilogram. Then temperature rises. They found that rises from 35 into the input into 92, and then this is the maximum. Okay, so when they come to find the thermal energy or heat, this is the heat capacity given the question. Okay, mass, sorry, calculated, and this is the heat capacity, and this is the temperature difference. They found this amount of energy captured. If we multiply them by 12 hours, okay, it's really a huge amount of energy, enough to provide the needed hot water by the Omani family. Now, application of solar thermal, there is low temperature application, which is below 100 Celsius, and between 100 to 150, which is called medium application, and high temperature, more than 150. For more than 150, definitely for electricity. For medium, we use them in industrial process, in refrigeration, and for low, it's used for small applications, solar dryer, hot water supply, cooking, and so on. As you can see here, the temperature here with respect to direct daily storage, and so you can see for large temperature solar cooling, agriculture in the middle here, and for heating, ventilation, small temperature at home or building. Now, you remember the spectrum, solar spectrum. We mentioned that the solar spectrum contains 3 parts. This is a visual part which is used by PV, but for thermal collector, no, it use both. infrared radiation and the visual, both of them are used here. The whole spectrum, almost the whole spectrum, is used to and captured by solar thermal collector, and then it can be heat water. In the past, as you can see here, this is from the past, they use it in let me say, in the war. They focus the light using lenses and they try to destroy enemy ships. Okay, this is called concentrators. Concentrator, we have mainly three type of concentrator: central receiver, parabolic dish, and trough. Parabolic trough. They concentrate the light on a point. As example, here they have mirror. As you can see here, this is central receiver. These are mirrors surrounding tower. Here the receiver, and the light coming from any direction from the sun will be focused on this point. Okay, it's heated more than 150. Okay, and also dish type, which is called concentrated solar power with dish type. This is the dish type, similar to the dish we use for internet, for TV. Okay, and light focus on this receiver. And trough system, we have two type of trough system, 1 and 2. As you can see here, this is the trough system. This is the one used in Oman in Mirat project, where they focus the light from here and here, here and here, here and here on these pipes which contain the fluid, or they can concentrate it up here, and this is another reflector, okay, connected here. So this is the trough, this is central receiver, and this is the dish type. It's used long time back, okay, in many countries. Now, for solar water heating, okay, the one used in many countries today for heating, to heat water used for showers or other application at home, we have either passive or active. From the name, for active, it means we're going to use sensor, motor, and electrical circuits. While for passive, no, it's used we do not use these elements, and it's used thermosiphon. As example, here you can see this is a tank, okay, contain this part is here explained. You can see here this is a tank inside this box, okay. There is glass in the top to contaminate energy, water, cold water coming from down, okay. It gets heated because the tank itself captures the heat from the sun and get heated, the hot water going up, and then it taken either to be used or it will be saved in a container, as you can see here, container, and used later on. This is the passive element. It's used thermosiphon usually they use thermosiphon. Here how they use it. Now this is the collector, they put it down, okay. The cold water coming from down, it's heat captured here, it get heated, the hot water going up by thermosiphon phenomena. It's go up and then go to the container here. Either it is used directly or it's go to another container to be used later on. Okay, this is how it look like on the top of houses. Okay, many countries are using this. Okay, now when we add a controller, sensor, and motor pump, okay, it become active. We don't wait. We can make the collector upper than the tank, the opposite, because we are going to rotate the pump itself. Now this is the active, as I mentioned. As you can see here, this is the collector itself here, and this is the pump, okay, rotating. Sometimes they use heat exchanger. Heat exchanger is like transformer in electricity, okay. Here coil and inside the coil, inside the tank here or the container here, there is a coils, two coils. This is another coil, okay, and there is fluid. The fluid coming here will give the heat inside to the fluid inside the heat exchanger, and then the other coil take the heat and then send it to the application. Now for cold places, we have either direct circulation system. This is when the climate is really freezing, okay. It's mainly used in countries where really freezing, okay. They use this one. Pump circulate the hot water to the home. But indirect circulation, what happens, they use heat exchanger. They cannot directly circulate it, so they use heat exchanger. This is in a freezing temperature, okay. because they use fluid one side, they use, and on one side they use a fluid which cannot be freeze easily, okay, and the other side they use the water. And in drain down systems, when we have temperature drop to freezing, below freezing, I mean very low temperature here, what they use a electric valve to heat at the face, okay, it's here like herb system to heat the water phase or the fluid, and then it use the energy coming from the captured from the sun to be to heat the water. It's used in many application. Example here you will see this is the heat exchanger, the collector here on the top, and this is the heat exchanger. You see here the hot water coming, okay, and it gives the heat here, and then it's taken from here to the application. Or as example here it's used in cooling to cool the swimming pool. It's used in many countries actually. Now if you go to Europe as example, where it's cold, less energy, solar energy available there, but still you can see on the top of their building or houses, the roof there, there are many collectors. As I took these photos from different houses, okay, and the type of collector, as I will mention later on, is the collector, the pipes inside the collector is taking different shape, and the shape will specify how much energy each one of them has, its advantage, disadvantage. There is another type of solar water collector beside the active passive. These are the flat plate one. There is what we call it evacuated tube. Evacuated, more efficient, more effective, okay, comparing with the previous one. What we have this is how it look like in general, how it look like. Pipes, it's cylinders, okay, this is the same thing you can see here, cylinders. One, let me take one of them. This is the cylinder from glass. Inside there is sheet, as you can see here, this is the sheet, we call them fins, okay. Inside these fins connected from metal, connected to pipe, and there is a small pipe inside this pipe. The current following here inside this, the internal pipe, and return back from the external pipe where it gets heated, okay. Fins help to capture more energy. You can see here they use them to make a shadow, okay. The fins themselves make a shadow in some countries, as this is the shadow for park, okay. You can see these are the pipes, vacuum tubes. You see here, this is the glass, these are the fins, the water coming from here and internally and returning from here, okay. You can see this is a comparison between a flat plate, the black one, how much energy it gives for the same system, and this is the vacuum tube one, how much it produces. There is another collector also using this vacuum tube. It's called heat pipe collector, the U-type. U-type is similar. You can see here, this is the U-type. They cover it with a metal inside, and there is one for water in and one for water out, similar to this one, in and then here out. It's also heat the water and used for domestic applications, okay. I mentioned for using solar thermal for ventilation, and we can capture it by this well, and there's glasses here, hot air coming up, and then it's go inside the rooms. This is the trough, parabolic trough, with the one we use in Oman, similar to this one in the art project. As you can see here, this is PDO project 50 mega with let me say with glass point company. Here are some solar thermal applications designed by our students. As you can see here, this is solar water heater, desalination. We have the water, salty water coming here and desalinated using air concentrators. These are different designs, separate designs by our students. They graduate long time back. And this is CSP also. This is another solar water heater, solar cooker, okay. So we use the heat to generate our needs, to generate energy need for our needs. Now if we compare countries installed capacity in megawatt thermal, okay, talking about here 15,000 means 15 giga. It is really huge. You see China, they use they up to more than 15. United States, Germany, oh, many countries are using this. And if we would like to break it down to see how much the percentage or flat plate or air collector or any glass